In some ways, this is a bit of an anticlimax. There's many ways of deploying such a model. You could deploy a model on the cloud, you could deploy a model in an embedded system running on a CPU or a GPU or an FPGA. Purely as an example, we're actually going to show it deployment using TensorFlow Lite. So TensorFlow Lite is aimed at inference environments where we're actually going to be running our model in an environment that's memory limited or limited in computational resources. Anyway, this is purely by way of an example. So the important point is the back-end flow is always the same and it's always different. It's always the same that in the sense that in the context of edge computing or embedded systems, there's 4 steps we're always going to have to follow. But these 4 steps are different for every vendor. So the first thing we're going to have to do is to take our fully trained model out of our training framework and do some kind of format conversion. Then we're going to have to do some kind of weight compression or model compression in order to reduce the amount of memory we use to store the weights in the target system, or to simplify the computation being done so that it can run efficiently if we're using a relatively small processor. And then finally, we're going to have to compile our model and generate code. And that step could look very different depending whether we're using an MCU or a GPU or a CPU or an FPGA or a specialized hardware accelerator, whatever it might be. And this is where it's really, really important that you use the back-end flow that's specific to your particular silicon vendor. So check out the flow provided by your particular silicon vendor and make sure you use that flow. You don't just use a generic back-end flow if you're targeting a specific MCU or a specific neural network accelerator, for example. However, the details are going to look very different depending on the actual backend. So the takeaways from these slides are relatively limited. Unless you're using TensorFlow Lite, the details here don't matter so much. Anyway, what we do is to take our compiled Keras model and convert it to TensorFlow Lite. Then we dump out our TensorFlow Lite model to disk, in this case using pathlib, which is another standard Python library. Then we can perform quantization. So quantization means converting 32-bit floating point values we used for training to 8-bit integer values that we're actually going to use for inference when our model is actually deployed on an edge device. So we're setting up our model for quantization, and quantization actually, it turns out, makes use of a calibration data set. So we've got a calibration data set here to pick out some random values from our test data set. Again, you can copy and paste this code for yourselves if you want to reproduce this example. Then we quantize the model for 8 bits. So we do that by calling converter to convert and write the quantized model out to disk. And now, just for the sake of it, we can compare the sizes of the original and the TensorFlow Lite and the quantized model. So it turns out the TensorFlow Lite model is about 1/3 the size of the original fully trained Keras model on disk. And then the quantized version of the TensorFlow Lite model is approximately 1/4 the size of the unquantized model. So we've reduced our memory footprint required for storing the model and the weights by a factor of about 4 by quantizing the model. We can probably do better than that if we're even more aggressive. So we can now use our quantized model for inference in our target system, which could be on an embedded device, could be in the cloud, whatever. So to actually do the final inference bit, this is going to look very different depending on your actual target device, but it's probably going to look equally simple. So here we're instantiating our TensorFlow Lite interpreter. Then we set up a test image as input data by setting the test image, the input data, in the appropriate location. We actually run inference with a one-liner, interpreter.quant invoke, which actually sends the test image into the neural network. And then we extract the result. We get out the prediction from our final quantized deployed neural network. And we can now sanity check the result by plotting the prediction. So if we plot the image using matplotlib. We can see we actually fed the image of a lemon into our network. And now we compare the prediction of our model with the ground truth, the label. Converting the one-hot outputs to integers, we can see the ground truth was label 104, the prediction was 104. So there we go, bottom line. Our model worked, and after we deployed it for inference, we sanity checked it with a data sample, and it gave the correct result.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of John's webinar using Python to implement a complete machine learning flow whenever you want, by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.